get started. So I had a few problems just getting the right titles for this talk. So it was either going to be Rise of the State Machines, which I realized really quickly was a pun that somebody else pulled on their article, so that didn't work. Then, oh, the clicker is not happy with me. Is there a reason the clicker wouldn't like me? You didn't have two of them. What's with you, clicker? Well, too bad. I don't need this. All right. The other idea was this, right? That kind of is a weird reference that nobody will get. Another band reference, right? Cool. And then for the really old prog rock folks, that might be a lost reference on most of you, since you probably weren't born when that band was still playing. All right, cool. So, what is state? So in computer science, as Wikipedia tells us, it's a system. When you describe a system as stateful, it's designed to remember preceding events or user interactions, which is most of what we do when we write software. The remembered information, that's what you call the state of the system. So a simple example would be something like this, as simple as it kind of gets. A light bulb is either off or on, right? So that's our state. You notice I sneaked in a little bit of UML in here. So what's a state machine then, right? Is it super complicated? I Googled it and Wikipedia came up with this. I started reading and it gave me a slight headache. But the important part is right here, and that's the one we're going to focus on today. So to paraphrase it a bit, a state machine, it's a computational model that can be in exactly one of a finite number of states at any given time. So the light bulb effectively is either on or off, and not both at the same time. Okay, that's important to remember. We're not talking physics here. All right, so an event, also, an interesting thing to note, is something that happens and that will affect that system. So you can look at it as an event is a user pressing a button or turning the switch on or off. That's an event. And that causes a transition. You can also call them actions. Like I find the wording in UML state machines in that article to be super interesting if you've looked into the MVI pattern because it's effectively where it's coming from, right? Okay, so we're going to go from theory today to actual practice. So I'm going to be using code from this repository I'm linking to down here. I hope that link is visible. So that's part of a course I built for a website called caster.io, but that sample is definitely public and definitely open source. So it's an adaptation of the Android architecture pattern. So just a show of hands, who's familiar with like the Google architecture, Android architecture patterns, the website? Some people in the audience. So that site basically shows you how to build a to-do app with most of the patterns, architecture patterns that are out there. So you're going to get MVVM, yes? Wow. MVVM, there's no MVC, there's going to be an MVP, model view presenter, in there. There's a few others. Most of these samples use Android's architectural library APIs. So those are really good examples if you want to dig into what Google offers as far as architectural styles go. I felt that these things were super interesting, but I have my own personal stack of choice when I build apps. So I built my own version of this for the course, only using effectively RxJava to create streams and things like that. But the core of it is the state machine. And to be clear, you don't need to be in love with that MVI pattern to use the state machine pattern that's in there. That state machine pattern applies to basically whatever architecture you might be doing in your own apps. Okay, so our first state machine use case is going to be the pull to refresh. So I pull the screen, some sort of process goes on, we refresh the screen, and we show a list of to-dos, right? Pretty straightforward. So how would we go to model this in a state machine? Well, we have effectively two states with a third one that might or might not happen. So when the user has not yet pulled to refresh, we're in what we could call idle mode, right? We're not doing anything specific. Now the user might pull to refresh, and that's our event, our action, our transition. That's going to bring us into another state, which is a state that will be process or processing. Our app is doing some sort of work in the back. That's the meaning of this. Now, once we start loading, we're either going to, well, we're probably going to hit an endpoint on the web, excuse me, and we're either going to get a success out of this, which will bring us back to the idle state with a new list of components, but we don't think too hard about that right now. We just focus on that specific call to the website flow, and that call might fail. So another possible state that comes out of this is we fell into an error state, and we might want to display some error message to the user, letting them know that we failed to refresh the list and to sync up with the server. So this is how I recommend, and how I personally anyway, code my state machines in Kotlin. So I used the sealed class pattern in Kotlin. So who here is Kotlin day to day, day in, day out at work? And who's still on Java, effectively, for Android stuff? Who's not at all into Android stuff? All right, we have a good mix, right? So the thing with Java is I used to take this approach also in my Java apps. I'll spoiler alert right now, it's not great in Java. And not because the pattern's bad, it's like quite nice, it makes quite solid apps, but you will end up with a ton of boilerplate if you try to replicate this. Come talk to me after. I have really old repos where I tried this stuff, I can show you. But yeah, it's a bit, yeah, you have to like reading a lot of Java. Anyway, but the fun part about Kotlin here is that sealed classes are effectively like enums, except that you can define different components of this enum. So we have a good sampling right here. Like the first possible sealed state you get into the sealed class, the object idle, in this case is a singleton. It's not even, it's like effectively like a static object that's available to your whole app. Then the reason we can do this is that idle itself carries no information, it has no parameters, it has no extra state to think of. It's just, we're idle, we're not doing anything, and that's that. So we can get away with using object here. That's slightly different if you think about the processing state. That processing state is basically saying, okay, I'm doing something, and in this case, we might want to add an extra type of information to this, right? So if you're processing that generic name, you might have wondered, why is he using such a generic name? It's because in my little design, I decided that process meant anything asynchronous going on where I'm going to be showing a spinner to the user. So I'm going to be showing a spinner potentially to the user if I do a check mark. I would typically wait a little bit before showing a spinner. Like, it depends what you want to do with your UI. It might be obnoxious if every time you press a check mark, your UI starts saving, right? But effectively, if you're launching an asynchronous process and you want to capture that, you're going to need extra information with process. And that's a type of process in this case. Now, that's just a convention I decided for here. It's like an example sake, right? You can structure your things differently. But the important key point is to remember that we're using a data class, and that will have an instance of its own, and it can carry extra information that you can decide to bundle it in there. And the very last data class we have here is error. So in this case, I decided all I needed to have is a throwable that caused the problem, and I would use that to report to the user whatever happens, or etc. Right? Right. So we're going to be jumping into code in a second, but I do want to provide more context here. So to-do apps are pretty straightforward as things go. This one is fairly straightforward. It has a few weird screens, like it has this concept that you can edit a to-do, which is not necessarily something I would do in a different screen if I was making my own UX for a to-do app, but it is a bit of a contrived example that's pretty practical for us if we want to sort of study different ways of doing things. So our to-do list right here, we have milk and cookies we have to purchase at a store, presumably. So you add things to the list, you check things off, you might delete some things off that list. So if we start thinking about the model behind this app, we're not only going to have a model that represents what we're doing, right? Like I've only showed you a state machine that represents if we're doing something asynchronous. In reality, we're going to have extra data that we're going to want in there. So in this case, we want a list of tasks. And alongside that, we want to know a little bit what's in the task. So we have an ID, typical computer science stuff. We have a last update, which is just like a timestamp information. title, description, and we have a Boolean that says if this task is completed or not. Fairly simple. So once we start thinking about connecting our app to cloud storage, then we need to think about this sync state I just showed you, which is our first example of a state machine really here, right? So we see all the states that we saw earlier in the diagram. And when we pull to refresh, we go through that cycle. So if you remember, of course, the cycle's right here. It's not that long ago I showed it to you. So now what we're going to do is we're going to jump into the app and look at that actual, the actual usage of the state machine with little breakpoints and try to pull to refresh and see how things update and what happens. All right, so first off, I wish there was a shortcut button. If you know of a shortcut button that allows me to do this in one click, like, come see me after. I'd really like to learn it. Cool. So we established that this was kind of readable earlier. I don't like the small font on the side, but we're going to live with it for a little bit. All right. So small plug for a tool I use that I find very useful. It's called Plant UML. It's a really old school tool. It's like available without IntelliJ. It's a plugin in this case, but it's a tool that when you start typing in your documentation things between the start UML and end UML tag, you generate these nice little diagrams on the fly. So that allows you to document your app pretty nicely. Now the bonus here is that you can actually export these to SVG. So if you do open them in an external editor, for example, like I did right here, you could get something like this. And you can start mucking about with the diagram, whatnot. Anyway, I've always found it like a really nice little tool for documenting what the heck I'm doing. And with state machines, it's actually a very good idea to do this exercise and go through the diagram. It'll, as we'll see in a bit, it will help you think through all the possible cases. Because in a lot of cases, if you just think about it like offhand, you end up missing some bits and only realizing that once you hit the problem somewhere in your UX. Anyway, so in this case, we're interested in looking at how that sync state machine is working. So we're just going to look up where we're accessing it. Oops, what am I doing? Right. So in this case, I also have a demo of test, but I decided not to go through that today. I just wanted to really focus on mostly not this, the actual app itself. So I'm going to run the app first. It'll be easier to visualize. We've started the run process, and Android, true to itself, takes its sweet time to build. All right. Okay. All right, so we're in our app. I'm going to check my breakpoints, show you where they are sitting at right now. Like, oh, interesting, Dart breakpoints. I don't even remember doing any of Dart. Okay, so we have this call here, which is the build reload task intent. That's something out of MVI. You don't really need to worry about what an intent is, but as far as like the state machine diagram I've showed you so far, you can look at it as the point where we're transitioning from one state to the next. Like this intent is built and executed whenever the user does the pull to refresh gesture. So that's where our function is going to get called. So this is the part where we're preparing the work to be executed. And then we'll be executing it. So by putting a breakpoint here and doing the pull to refresh, we're going to intercept that action while it's happening, if all goes well, of course. So let's see. Of course, you have to start your app in debug mode, right? That would help. All right, let's try this again. All right, there we go. So what I'm doing here is somewhat important, like the assert call. And this is not something you typically see in Android apps, and I'll explain in a few minutes like how to do a better approach at checking your state and your transitions. But right here, this serves our purpose. We're checking first thing. If we're really attempting to do a reload operation, it would be a very weird thing if, let's just bring that diagram up again. Like, if we're not currently idle and the user manages to pull to refresh, what does that mean? Would it mean that we're currently already doing something and we let our user do a pull to refresh? So let's imagine for a second that we check the check mark and we're doing this asynchronous task. So if you remember in the very first slides, I mentioned how state machines are only in one state at a time, right? That's where I showed Maru the cat, right? Don't be the Schrodinger's cat. Like, you're not supposed to be doing this. One thing at a time. And also the right thing at the right time. So if you're trying to do a new process, you can't be calling the refresh transition if you're already processing, right? If you see the arrows in the diagram, that would make no sense. So we enforce this by doing an assert check and effectively just breaking the app if ever this did happen. This is what I call, when people ask me, but this is sort of makes your app brittle, doesn't it? And I'm, no, this is a developer problem. This is like an actual programming error. Either you have a way of handling it, and in this case, you don't. You want your app to crash. That's the whole point of crashing. It's just to say, hey, things are wrong here. You should fix that, right? So that's what the assert does here for us. It verifies that we're in a valid state before we try to move onto the processing refreshing state. All right, so now we defined other things for retrofit right here. So we're going to be saying, okay, what happens if we have a success? We have this function that will get the result of the success, and then we'll chain that next transition, which will assert that we were currently processing, that we were refreshing. So if you look at the diagram, this is code that will get executed when success happens. I hope you can see, yeah, you can see the arrow very well right there. So when a success condition happens, this is the code that we're going to run. And this code is going to double check that everything is in the correct state before it actually tries to do this. Right? And again, if there's a programmer error in there, it's going to crash, and that's what we want. So how do we transition from one state to the next? We use the copy operator right here, the copy function. So what's going on right here is that from one state to the next, copy will take current state, which has, like, if you will remember the diagram we showed a bit earlier, I'm going to just bring it up again to make that very clear. Like, I showed you this diagram right here, right? So if you remember, we had the master state right here, task lists and sync state. So this is what we're playing around with right now. So we're making sure to copy the new tasks into the state and to transition from a sync state of processing with refresh into idle. Now we also will define here what happens if the retrofit call fails with an error. So we're creating a function that we're passing along. We're not running this code yet, right? So we're creating this function that will also check that we were processing with a refresh, because if we're trying to error out a retrofit call and the system is not in an expected state, we have effectively an illegal state going on, and we want to flag that. So by doing this check, then we're good. We know that we were trying to refresh and we failed with an error, and then we will update our state to reflect the fact that, hey, we got an error. Now this is a handled error. This is the proper way to handle errors in propagation when you're doing state machines. Meaning that your code that listens in on the state changes, your UI code, will be able to say, oh, that wasn't an error. I should put up a toast or something. Probably something better than a toast. All right, so, and to finish things off, right here, what we're doing is we're doing the actual retrofit call. Now we're using RxJava, so I'm gonna ask again for people to raise their hand. Don't be shy. Who here is not comfortable with RxJava? And please raise your hand, because I expect it to be at least a third of the group. Okay, I'm surprised that there's no more people. But I'm pretty sure that most of you are familiar, if you've done Android, with retrofit. So retrofit does not force you to use RxJava, right? So you could use the same style of error handling even if you do not use RxJava with your retrofit calls. Here we are, so it allows this very terse way to say, okay, when I subscribe this call, if the call finishes in a success, right? Then when this task completes, please call this function I just defined above. And if it fails, please call this, right? So all our transitional states in our state machine are covered by this, neatly with a little bow, and crashes everywhere else, which is what we want. Again, remember, legal state is bad. You need to punish that really early in your development process so it doesn't go out to the customer. Okay. The other things that were going on here was that the actual REST API call was just this simple function, get tasks. We mapped it to a values to list here, so we made the conversion of what we got from the web to make sense for our model. So that's like meat and potatoes pretty much. Schedulers IO, that's how you manage your thread game with this stuff, but I'm not going to go into details here for that. All right. So that was how we do state machines first attempt. Now there are some problems with this approach. Now we're still in debugger, so I'm going to actually sort of just finish that debug loop to show you that what actually happens, right? So just to understand very clearly, because sometimes when you define inline functions, that can be kind of confusing if you're not used to this programming style, and I totally get it. This is not new to me, it was, so it's not always easy. So the thing to understand is that we create these functions here, we don't execute the code. What we do is we pass the puck to retrofit down here at line 101. It will decide which function to call depending on what happens, and then we move on. So I'm putting all these breakpoints there to show you that's what's happening, and hopefully that's not going to behave weirdly. So right, we skip right from this assert that indeed checked that we were idle when we tried this operation, which just makes sense. Then we get to the point where we're going to do the retrofit call, so we execute that. Now we've just finished this, it's running asynchronously, so we do need to keep moving. So what we're doing right here, and that's kind of a key point, the retrofit call, it's off on another thread right now. But before that thread can do any type of work back on the main thread, we have to finish what we're doing. So this is what guarantees 100% that our whole state machine is going to be sensible. Meaning you don't try to mutate the state machine or to make it transition, because mutate is maybe not the right word for this. But you can't have two threads at the same time trying to transition your state machine. That's impossible in our setup. The transitions will always happen on the main thread and will be very quick, and that's nicely behaved, and that's what you want. So the first transition we're going to do, because we haven't done it yet, is to transition our state machine from idle to process refresh, which is what that call will do right now. And when I hit run at this point, the next step should be a retrofit, either success or error. And in this case, it's a success. So we got our proper payload back. We're going to assert that right now the state machine has transitioned from idle to processing with refresh. Otherwise, we're going to crash right here. So again, you can see that these asserts are not a bad idea, because if ever the state did not make sense, it means you screwed up your threading somehow. And we need to catch that right away. Right, so things were good, we copied the state, and we can see on the right that the state machine updated and the UI updated following all of that. So that was a lot of stuff, but not too much code. And well, actually right now I'm going to take a minute, field questions about this, because I want people to be comfortable with these concepts. And you also might not be comfortable with asking questions right now, so it's okay to ask them after. But right now, if anybody's feeling gutsy and wants to ask a question in front of everybody, please do so. Yes?
Why do you update the state Kotlin?
Sorry, I did not hear you very well.
Why do you update the state, so the sync state, to screw copy? Because you do a copy sync state process.
That is a good question. So, that's something I did not cover that I usually cover in my MPI talk. So one of the tricks with the way I operate with state, and that's a personal choice, you might not subscribe to this religion of sorts, but all my state is typically immutable, and that's a big thing for me. So why are we using copy? So I'll jump back really quickly to the task state definition right here. Okay, so we see that task state itself is a data class, and sync state has data classes as well, right? So what's fun with data classes, well, first thing that's fun is that they're immutable. So you can't have one copy of a data class and mutate it. Now, why is that a good thing? So what it guarantees is that if ever you did have problems with your threading, it's impossible, effectively, for somebody to mutate process in the background somewhere and trip up the state machine or trip up anybody else that's depending on that actual thing. Now, immutable is all nice and friendly and all of that, but we are dealing with a state machine that transitions from one state to the next, right? So you do want some way of changing that state, even if mutability is not something that's desirable here. So that's where the copy operator comes in. It takes your data class instance, and what it will do is instead of mutating the current one that you have on hand, it creates a new one with the actual attributes changed to whatever you decided to do in the copy operator itself. So if I jump back here, that copy operator takes the old state, changes the sync state inside of that, the sync state attribute, and changes the tasks list and creates a new one. So that also means that if anybody else is currently holding the old one, that's fine. They're going to get a new one in due order, but they're not going to get something that changes under them while they try to access it between two calls, right? So that gives you that thread safety that you really, really want. I hope that's a decent answer. Did anybody else have a question at this stage? Don't be afraid, we'll have more time for questions later. Don't worry about that. All right, so going back to the slides very quickly, because we don't have that many left. I think I have like one more, right? So I'm going back to this idea right here. We have the list, right? That's cool. So the next thing we're going to want to do is to sort of improve on that state machine I just showed you. So, because there are some problems with what I just showed you. And namely, it's how we control the transitions between the states. Because really what I showed you was a list of tasks with a small state machine inside of it that was only concerned with what was going on with the asynchronous processes that we're calling the web back and forth. But we want something a bit fancier than that. And I came up with a pattern in my apps that I like to share with folks that I think is kind of interesting. So when we press the plus button on this to-do app, what happens is that we create a new to-do. It's a bit of a contrived example because if it was my to-do app and I was shipping it to the store, I'd like that to happen in line in the list and be all cute and nice and friendly. But in this case, we're actually popping up a new fragment or activity to actually do that in a separate window. That's mostly to show people like these different ideas of state management. Well, for me, that's why it's there. Originally for the architectural patterns, I think they also wanted like a bit of a beefier example with more screens to show how transitions work and all of that, right? Okay, so what do we have here? What can the user do on this screen? So the user, if you want to formalize it as a state machine, we're going to do so right now. We're looking at what you can conceptually call a document. Now, it's a to-do, it's a big word, document, for like a one-liner to-do, but let's just call it a document. So conceptually, a document, if you think of it as a Word document, sorry, I want to laugh just saying this, but whatever. So if you think of it as a Word document, this nice little to-do, then it would either, well, you start in a state that's typically closed. So right now, we're sort of not exactly doing what I'm showing because in a sense, you have two choices when you're starting a document, right? You're either creating a new one or you're editing a currently existing version. But effectively, for our example, let's just think of it as closed when you start off, right? So when you're, actually no, sorry, the example's not that bad. You have to think of the state machine really more as the screen. So let me just pick that back up. So the screen itself, the editor is closed, in a state that's closed. Now, you have a couple of transition points that are possible from this closed state. You can either start adding a task, and I wonder if the laser pointer works. So, well, the mouse works, right? No, it doesn't. All right, so laser pointer. Is this visible? Yeah, okay. So we're starting with closed, so we can either add a task or edit a task. Those are the two only things that are possible. And that state closed, really, that's the state that we were in when we were looking at the list. We're not yet editing anything. So when we're looking at the list, we can either click on an existing task or click on the plus button, which will give us a new task, which is what I showed in the animation. When we do this, in either case, we end up at the next state, which is editing. So what happens when you're editing a task? Well, a few things can happen, right? You could click here and start editing that text field, which is the title, or you could start adding a description if you really feel it's worth it, right? You can do these things. So any type of edit operation, in our case, would be mapped as an edit transition. And what that means, sorry, no, it's not going to help you. No, sweetie, no, it's not working. Okay, she tried. I almost want to call out applause for her, but let's not do that. Okay, how to totally derail the presentation, but that's fine. So when we're editing, effectively every time you're typing a new character in here or in here, it's an edit operation. You're adding something to the model that currently exists in memory. And what I've done here, the way I've mapped this out for my app, is that the task itself under editing is held here. That task is as you'd expect, like it's the structure we showed earlier. It has a title, description, a last update time, all of that nice stuff. And every time an edit operation happens, it's going to take the task, it's going to do that copy operator on it, create a new instance of it, and reassign it to the editing sort of holding state. Also through copy, but we'll see that in code in a second. The other possible thing that we have here as its own internal state is error. So why is that there? Well, that makes sense if you start thinking about the next steps after editing. So once you're editing a task, when you're done, you're either going to press on that check mark right here, or potentially press the delete button, which will only activate, by the way, if you're editing a task. When it's adding a task, you have to detect that and not make it light up. There's ways of doing that that are in the sample, but anyway, I won't go on too much about that. But, right, so when we're here, you can either save or delete. And we can imagine for a second, it's not the case in the sample code, but we can imagine in a second that these two operations could be calls to the web, asynchronous calls to the web that could potentially fail, right? So if you look at them as asynchronous operations, when you start the delete process, you're going to have something very similar to what we did with the refresh process earlier. You're going to enter this state that's effectively a waiting state for something else to complete, either with an error right here, or a successful deleted or successful saved transition, okay? So what you're doing here is you're covering all the possibilities of what could happen when somebody's using this screen and how the data underneath is changing. We're really being super explicit about where are we going from A to B, and the exercise with this diagram, depending on your app, might be very different, but the exercise is you're gonna map out all the possible transitions, and you're gonna make sure that they are present and thought of, and that everything has a clear resolution. So specifically, think of errors, right? It's only one way to handle errors, meaning if the process fails, you could throw the state machine back into editing, adding this error information, and keeping what task you had in memory, right? So this could be very good if you're either saving or deleting, if, for example, the network is down. If the network is down, that error is effectively going to say, oh, I tried to save your work, user, but the network is down. And then you're going to show up that editing screen again, right? So the user could decide at that point, screw this app, like, I've just lost my work. I can't save because I don't have a network. Or in this case, just find a Wi-Fi and then hook up and then make sure that the work is saved. Like, what I'm trying to point out here is that in my model, I'm not being very safe-ish concerned to Wi-Fi loss. Like if I was making a more serious app, I might consider finding ways of persisting the work that the user has done and updating it later when I have network and allowing the user to leave this screen without losing their work, right? Because what I'm doing right now, the only thing I allow the user to do if I have an error is to cancel out, and then cancel transition here is something we hadn't talked about yet. It's when you press this button, right? But effectively, in the way we coded this app, or I coded this app, when you press cancel, if you had a network error, you just lost your work, which is, well, in this case, not that terrible. But if you were filling out your tax forms with this, then that would be a bit less optimal. I'd have to think of a different type of state machine to save that state in case of an error. But that's my whole point. These kind of approaches, they force you to think through all of this ahead of time. All right, so we've gone through that ad nauseum. Any questions about this flow? Because at the end of the day, it's just an example, but you might, we're good? All right, so we're gonna go through the code and see how that's implemented in the sample, and what are like the approaches to doing these little transition calls, which are a little bit more efficient than the async checks, not async checks, the asserts, thank you. My brain's just like asserts, it's got S's in it. It's the same as sync, isn't it? Okay, assert, async, cool. Anywho, so we're back to live demos. I'm gonna jump back into IntelliJ, bring back up the sample. So I have to apologize, I was a bit rushed. I have not yet put the breakpoints for the editing part, so I'm gonna jump in there and do that now live. But I will look at a little bit at the structure. I figure it might not be a lost cause to do this, or a lost time to do this, rather, because if you do make the effort of going and fetching this code from GitHub, it's always kind of nice to know where to find the classes and everything. So the way this project is organized, I'm going to walk through it. There's a few packages under the main app. So we have DI stuff, which you can ignore for now. We have intent stuff, which is not what we're interested in right now. We have the model, which is where most of the work happens. And the place we've modeled this diagram I just showed you, which is the first place we're going to look at, is the task editor state versus the tasks, plural, state, right down there, which is the list and everything we've seen so far. So the tasks editor state right here. So I'm just going to bring back the diagram that we had. There we go. Right. Close this. So I find I like this. I don't know if it speaks to everybody, but I do like having that UML diagram right next to the code that describes it. Like, I'm really sold to this plugin. It's really lovely. Anywho, so this is how I encoded this state diagram in my code. So again, I'm using the sealed class, which is like the magical enum thing that Kotlin gives us, which is really wonderful. Now, we start off with, again, another singleton, the object closed. Now, anytime you see object, you shouldn't be seeing attributes in there unless they're really static and permanent constants of sorts. It would be really weird. So what I'm basically saying is that closed, we get away with using object here in a single instance because effectively closed does not carry any other information in it rather than its own self, right? So if your task editor state is closed, there's only one type of closed that's possible. You can't have like 5 different ones. So the big difference with the previous example I showed you for the state machine is that we're actually starting to encode the transitions right in there. And that's the key point of the whole pattern. So we have 2 possible ways of exiting this, right? We have add task and edit task. And very much what you see in the UML diagram right here. So there's no mystery here. What's the only mysterious pattern if you're not used to MVI is this idea that you're using reducers to basically go from one place to the next. So if you're in closed state, the way you transition from that is having the closed state on hand and calling add tasks on it, this function. So this function is the only way for you to get hold of editing and transition from one step to the next because of the way I've encoded these transitions, which I'll show right after we've shown this structure. So these transition functions, the key point right now is to understand that these transition functions, you define them at the state level itself. So it's a nice way of finding your way around. Like you just follow the path, and if you have the UML diagram next to you, it's a very effective way to define a state machine. Like I've tried to do this in Java in the past, and it might be that I need to learn new tricks in Java, honestly, because I've been doing it so long, at some point you become stale. But I've never managed to encode transitions in such a neat and tidy way in Java. Like typically if I tried to do something like this, it would end up being a class that's like 200 lines of code long for some reason. I think that sealed classes and things like objects and data classes are really what makes this magical in Kotlin, and a pattern I can actually recommend while keeping a straight face. Because this is not that long to code, right? So from add task and edit task, we get editing. So the idea of transition functions is that they always will give you the next state. And that state has to be a child of the task, the parent state, which in this case is task editor state. So when you get your new editing state, you can then transition from that in the following ways. You can transition by calling the edit function right here. Now I'm pulling a little bit of Kotlin trickery here by doing this. This allows you to call edit something like you can call your edit functions like this by passing in functions, right? So that's kind of cool. And by doing this, what you're doing is like inside that edit block, you're going to be effectively saying what you want to do to the task that you have on hand to bring a new one in. So I'll show you in a second what that looks like in code. But this function effectively transitions from one editing state to the next one by making changes to what's held by that state, which is this task. So once that little complicated bit is gone, what you have are simpler examples like save. If you want to transition from editing to saving, you call the save function on editing, and so on and so forth. So all your exit point, all your transitions are functions on your existing state. So that ensures that it's actually impossible to go from editing to saving unless you're in editing in the first place. You need to have a copy of the current state to go to the next. So all the assert calls I showed you earlier, as you can expect, are no longer really there, or they're going to be easily abstracted away. Cool. So saving, saved, deleting, delete. So you get the idea. Let's see what this looks like in actual action. So I'm going to just quickly look at, I think the edit function is probably the best one. Like I'm looking on time. So I'm going to show off editing and maybe cancel just a couple of these calls, and then I'm going to open the floor to questions, and then we can chat later. I don't want to spend I don't want to go over my time too much. I know how that goes. All right, so I'm going to look at who's using the edit function. It's really tiny right here. Like if you're curious also, I recommend that you check out the code and you go see the tests. Like this approach is also super testable. It's really nice for that. Okay, so we're just going to put these breakpoints right here so that the intent level, again, that's an MVI thing, but that's cool, no worries there. So we're just going to put these breakpoints there. And maybe another one for saved. Where's the saved state? Well, I'll just put cancel here. That's fine. All right, cool. So let's just see what that looks like. So my debugger should still be active, so we're just going to try to edit an existing one, perhaps. Let's see, this one here. All right, so I just clicked on Kale in my list of things to buy. So we can see that this triggers the build, edit, title, intent. So this is intents, again, are sort of what you want to do to your current model. And the idea here is that the actual act of clicking on that list item generates this intent, and this is the kickoff point to transition from one state to the next. So I've used a few Kotlin DSL tricks here to create an edit function like that, right? Like I mentioned earlier how that passing of the block here is used. So what we're doing here is effectively only focusing on the work we want to do on the actual task itself. So we call this edit function. It assumes a few things through this other little function right here. So we're building editor intents, and these editor intents, if I jump under the hood a little bit, they're actually a little bit complicated to parse. I'm not going to go through it right now. The key point is that this is a generic function that validates that what you're trying to do makes sense right now. So it's effectively doing the same work as those assert blocks I was showing you earlier, by verifying that if you're attempting to do this operation, that the current thing that you're trying to do it on is actually there under you. So what we're doing here is like, we've just said we want to get into an editing mode, and if it's not actually where we're at right now, just throw the illegal state exception, right? So what we might be also curious to see is when we actually, when we actually hit the copy function itself. So I hope I'm not losing you guys all too much right now, but anyway, we'll see. Okay, that breakpoint is not helping me out. That's fine. Wait, is it actually? Oh, yeah, anyway. My story made no sense right now. These were called because we've just instantiated the two fields, so ignore that. I can explain it live afterwards, it's going to be easier. I'll just skip over that little fuzzy bit. All right, the point is that right now we are really doing the task itself of editing. So now if I do change this, right, the breakpoint is set up right here. That's when we're going to actually properly try to modify the state of the task and go through the whole loop. That's basically all there is to it. Now, I'm skipping over a big bit of this, which is how do you actually transition from one state to the next, and how is that held in memory and all that. So it's done through this kind of structure right here. Time-wise, it's going to be a bit terrible if I have to explain model stores, and honestly, I didn't want to get into that today too much. But the key thing to remember is that somewhere in memory, right, we're holding a copy of task editor state that we're working on. And every time we have a transition function, we take that old state, we apply the function that we just defined on it, and then we take that new state, and that becomes our official state. You have to really look at it as one spot in memory where one state after another updates, and the rest of the application can listen in on it. That's something that will probably be easier to explain if you want. We can do an aside and I can get into the guts of MVI, but I'm going to keep to my word and I'm not going to go too deep into that right now. So, double check my notes. I think we're basically done with the way that state machines work and those transitions work. The key point is to remember that you use functions that build one key onto another and just transition on that. And it's that simple, so to speak. All right. Check my last notes. So I'm just going to bring back the URL for the repo, which I think is of interest. And on that, I'm going to say thank you.